Going through Thomas Kuhn's The Structure of Scientific Revolutions. We're now in Chapter 7, although, well, Kuhn refers to it as Section 7. I keep referring to these things as chapters. Kuhn's calling them sections. I will probably absentmindedly continue to make that minor error. Chapter 7, Section 7, is on crisis and the emergence of scientific theories. Kuhn begins, all the discoveries considered in Section 6 were causes of or contributors to paradigm change. He's talking about those scientific discoveries that precipitate a change in scientific paradigm. Furthermore, the changes in which these discoveries were implicated were all destructive as well as constructive. In other words, going back to what he said in Chapter 1, scientific progress is not always cumulative, adding one new discovery, one more refinement of a theory, one more theory, one more piece of data to another until we get closer to the complete picture of the universe. No, sometimes we take an old theory and we discard it altogether and replace it with a better theory. That's how scientific progress often works, not by accumulation, but by paradigm shift. After the discovery had been assimilated, scientists were able to account for a wider range of natural phenomena or to account with greater precision for some of those previously known. So these paradigm shifts do improve our scientific understanding of the universe. They do allow us to make sense of more of the data of experience, to account for a wider range of natural phenomena, or to account for them with greater precision than previous theories were able to. But that gain was achieved only by discarding some previously standard beliefs or procedures, and simultaneously by replacing those components of the previous paradigm with others. This sort of scientific progress that gives us the ability to explain more of the universe, or to explain the old stuff we could explain, but to explain it better, this sort of progress involves throwing away an old theory, sometimes, oftentimes, when the scientific progress involves a paradigm shift. Etc., etc. Discoveries are not, however, the only sources of these destructive, constructive paradigm changes. In this section, we shall begin to consider the similar but usually far larger shifts that result from the invention of new theories. So this chapter will give more details on, on that particular part of the cycle that science goes through. Let's see if I can remember how I was using this illustration when I recorded the last video last week. In normal science, you have a dominant theory about how the world works, and that theory informs scientific investigations. And from time to time, there are puzzles that this theory is supposed to solve that it can't solve. It can't quite explain some of the data. And this leads to a time of crisis, which leads to a paradigm shift, and a new theory replaces the old one, which allows us to make better sense of the data, and then eventually that establishes a new period of normal science, where that new paradigm is now the paradigm governing the investigation of things. We try to interpret the world according to this paradigm and do it better. Okay, so what's he doing in this chapter? He's talking more about the shifts that result from the invention of new theory. So this chapter is on this section of this cycle. Skipping paragraph 2, because it demands large-scale paradigm destruction and major shifts in the problems and techniques of normal science, the emergence of new theories is generally preceded by a period of pronounced professional insecurity. As one might expect, that insecurity is generated by the persistent failure of the puzzles of normal science to come out as they should. Failure of existing rules is the prelude to a search for new ones. Okay, so this illustration, I hope, is clear. I hope it's obvious. I hope I don't even need to say this, but just to be safe, let's say it. This way of illustrating is such that if you look at any particular moment in this cycle that I'm perhaps oversimplifying by reducing to four sections: normal science, puzzles the science can't solve, a sort of crisis, and a shift to a new paradigm, the reestablishment of normal science. This is an oversimplification. Every moment in this shift, in this cycle, involves every other moment. So he's mostly talking about this, but in order to explain this, he has to go all the way back to this, to those puzzles the old paradigm can't quite solve. The failure of the puzzles of normal science to come out as they should is the prelude to a search for a new paradigm, which only happens over here. Now he proceeds to give a lot of interesting commentary on Copernicus replacing Ptolemy, on Copernican astronomy becoming the new paradigm, replacing old Ptolemaic astronomy. I will mostly skip over all this. There's one or two sentences I have underlined here. In this edition, this is 3rd edition, University of Chicago, page 70 and page 71, that proliferation of versions of a theory is a very usual symptom of crisis. In this preface, Copernicus complained of it as well. So maybe I should have said we're talking about crisis, actually. We're talking about 12 o'clock on this cycle. Well, it looks that way as I'm recording. I get confused about how lefts and rights turn out in these camera situations. I hope this isn't going counterclockwise on the camera, on the video. Normal science, puzzles science can't solve, time of crisis, paradigm shift, and then back to normal science. That's the cycle. So actually, he's talking more about the crisis here, but he's still talking, looking backwards to the old puzzles that led to this, and forwards to the new paradigm emerging. Okay, so what was his observation here? This is interesting. A common symptom of a crisis coming up is that old versions of a theory keep being multiplied. You can't just stick with one version of Ptolemaic astronomy. There are some puzzles Ptolemaic astronomy can't solve, and so people come up with different variations of Ptolemaic astronomy to try to fix it, try to make sense of it, and it doesn't work, and that's what leads to the crisis where we eventually realize that Ptolemaic astronomy is wrong. It's not just that we have the wrong version of Ptolemaic astronomy. We need to rethink the whole thing. We need to rethink the whole foundations of this particular system of thinking about astronomy and consider heliocentrism for a change. All right, let's go closer to the end of the chapter. He doesn't just stick with Ptolemy and Copernicus. There's an interesting discussion for a few paragraphs. Well, there's references to a lot of stuff. There's some chemistry. There is some Newton and some Leibniz and some my brain's freezing. Einstein. There's some reference to Einsteinian relativity versus Newton as well. Anyway, towards the end of chapter 7 or section 7, 1, 2, 3, third last paragraph of section 7. In each case, a novel theory emerged only after a pronounced failure in the normal problem-solving activity. Furthermore, except for the case of Copernicus, in which factors external to science played a particularly large role, that breakdown in the proliferation of theories, that is its sign, occurred no more than a decade or two before the new theory's enunciation. The novel theory seems a direct response to crisis. The new theory that replaces the old is a direct response to the crisis that showed that the old theory just wasn't working anymore. The problems with respect to which breakdown occurred were all of a type that had long been recognized. Previous practice of normal science had given every reason to consider them solved or all but solved, which helps to explain why the sense of failure when it came could be so acute. The problems, the unsolvable puzzles in the old paradigm that led to the crisis were old problems. They'd been recognized for a long time. And normal science had long assumed that these problems could eventually be solved. Which is why when the crisis comes, the old theory just doesn't work anymore. The sense of crisis, the sense of failure could be so acute. Failure with a new sort of problem is often disappointing, but never surprising. Neither problems nor puzzles yield often to the first attack. Finally, these examples share another characteristic that may help to make the case for the role of crisis impressive. The solution to each of them had been at least partially anticipated during a period when there was no crisis in the corresponding science. In the absence of crisis, those anticipations had been ignored. The new paradigm that replaces the old one is often anticipated even in times of normal science. Even in times of normal science, someone often anticipates the new theory that's going to eventually replace the currently dominant paradigm. But people ignore it. People ignore it because the current business of science is to investigate the world according to this theory, and they think it's working out pretty well. It hasn't been made clear to them yet that there are significant puzzles that this theory cannot solve. maybe I should try to put some of this material this way. A new paradigm, a new scientific paradigm, is often such that it could have been conceived, and was in fact conceived earlier when the old paradigm was dominant, but no one was, or almost no one, was able to seriously consider it until there was a very real, practical, professional need. The failure of normal science to explain certain puzzles has to lead to a crisis, and until it leads to a crisis, most people aren't able to, using contemporary idioms, to think outside the box. Most people are not able to think according to a new paradigm until there's some strongly felt sense of a problem. Until we reach this crisis point, even a clever theory that someone had thought of way back here is not able to emerge as a new paradigm. Not able to emerge as a new paradigm, even if someone had the idea long ago, until a bunch of scientists actually experienced the crisis of the old theory. Let's just go over the last paragraph of section 7, chapter 7. I'll mention that the second last paragraph is an interesting illustration of these matters involving Copernicus being anticipated by Aristarchus in the 3rd century BC. All right, philosophers of science have repeatedly demonstrated that more than one theoretical construction can always be placed upon a given collection of data. History of science indicates that, particularly in the early developmental stages of a new paradigm, it is not even very difficult to invent such alternates. But that invention of alternates is just what scientists seldom undertake except during the pre-paradigm stage of their science's development and at very special occasions during its subsequent evolution. Okay, there's a lot of material here. I need to comment on this before I finish the paragraph. Okay, so philosophers of science have repeatedly demonstrated that there are different theories that can interpret the same data. Okay, now that doesn't mean science is subjective. It does mean it's not fully objective. It means, or at any rate, it means this. It means that a scientific theory is not purely constructed out of the data. It involves some amount of interpretation, and other interpretations of the same data are often quite possible. And how do you know which interpretation is better? Actually, Kuhn is giving us a largely objectivist account of how you know. You know because eventually, if it's an improper interpretation, eventually it will lead to failure to interpret more data. It'll lead to those unsolvable puzzles precipitating the crisis. But all the same, there is a non-objective element. One interpretation of the data is dominant in science, and another is not. But more than one interpretation of the same data is at least possible. History of science indicates that in the early stages of a new paradigm, more or less over here in this cycle, those early stages, it's not even very difficult to invent such alternates, to come up with alternative interpretations. But these alternative interpretations are things scientists rarely try to do, except during the pre-paradigm stage of their science's development, and in very special occasions during its subsequent evolution. Okay, different interpretations of data are possible, but scientists usually just stick with the established interpretation. They don't usually consider alternative interpretations of data except in times of crisis, or in the beginning of their particular field of science. So long as the tools a paradigm supplies continue to prove capable of solving the problems it defines, in times of normal science, science moves fastest and penetrates most deeply through confident employment of those tools. The reason is clear. As in manufacture, so in science. Retooling is an extravagance to be reserved for the occasion that demands it. The significance of crisis is the indication they provide that an occasion for retooling has arrived. Science uses conceptual tools, and there's no need to redesign your tools when there's no need. It's impractical to try to come up with new theories for interpreting the world when the old theory is working. And it's only when a lot of people start realizing that there's puzzles that the old theory can't solve, precipitating a crisis. It's only when there's this sense of crisis felt by enough scientists that any significant number of them will even consider a reinterpretation of the data according to a new paradigm. All right, so next chapter is on the response to crisis. I will perhaps see you there. Thanks for watching.